Hi, this is our first lecture in Math 4200. In this course, we're following the textbook Basic Complex Analysis by Marsden and Hoffman. And the material we're going to talk about today comes from sections 1.1 and 1.2. It's not all of the material in those sections. Our topics will be, I'll remind you what the complex numbers are, and I'll tell you about the complex plane, which you may or may not have talked about before. We'll review addition, multiplication, and conjugation and division for complex numbers. The last two you may not be as familiar with as you are for the first two. Addition of complex numbers looks just like vector addition in R2 when you identify the complex plane with R2. Multiplication is more mysterious, but using polar coordinates, we will understand what multiplication means geometrically. Okay, so complex analysis is a foundational course in mathematics, physics, and a lot of science. In some ways, it's just like calculus because you're studying derivatives and integrals. And this is a rigorous course, so we'll use analysis such as you learned in 3210 and 3220. The difference between complex analysis and regular calculus is that the functions are functions of complex numbers, and the functions are complex number valued. So f is going, we'll be studying functions f from a domain in the complex numbers to a range in the complex plane. Wikipedia is always a good place to get an overview of a mathematical topic. There is a complex analysis Wikipedia page. As I said, today our focus is to understand the algebra and geometry of the complex plane. So let's do it. As a set, the complex numbers are just defined as the collection of all possible x plus iy, where x and y are real numbers. So, for example, if x was 3 and y was 4, you would have 3 plus I times 4. And we don't care where we put the I in such an expression, so we'll usually write it as 3 plus 4i, not 3 plus 3i. Two complex numbers are the same if and only if their real parts and imaginary parts agree. And so if you have a complex number z equals x plus iy, where x and y are real, then we say that x is the real part of z, and we abbreviate those words by saying re of z is x. And we say that y is the imaginary part of z, and we abbreviate that with im of z. So for example, the real part of 3 plus 4i is just 3, and the imaginary part of 3 plus 4i is 4. And notice, we call it the imaginary part. It's the coefficient of I, but it's a real number. Okay, two complex numbers are equal if and only if their real and imaginary parts agree. So if z is 3 plus 4i, that's the same as saying that the real part of z must be 3 and the real part and the imaginary part of z must be 4. You can add and multiply complex numbers. You've been doing it in a number of courses. Certainly in your differential equations course, you did a certain amount of complex algebra. And when you add x plus iy1 to x2 plus iy2, the real part of the sum is just the sum of the real parts, x1 plus ix2, plus x2, and the imaginary part of the sum is the sum of the imaginary parts, y1 plus y2. And when you multiply two complex numbers, this is the formula for how you're doing it, and it's just what you would get if you FOILed out the product on the left and collected the real parts and the imaginary parts subject to the following condition. Every time you saw an I squared, you would replace it with the number -1. So if you FOIL on the left here, you get x1, x2, and then you get also an iy1 times an iy2, which is an I squared y1, y2, and you just replace the I squared with a minus. And that gives you the real part of the product. And if you look at the other two terms from the product on the left, you will get an x1 iy2 and a y1 x2 times I. Okay, so the rule for complex multiplication is equivalent to just saying use regular arithmetic rules, and everywhere you see an I squared, replace it with a -1. Geometrically, we identify the complex plane with R2. So on the left here is a picture of R2. Here's a typical point in R2, maybe 2, 3, where we displace horizontally by 2 and vertically by 3. And we identify that point 2, 3 in R2 with the point 2 plus 3i in the complex plane. So in the complex plane, there is still a horizontal x-axis, but the vertical axis is now called the iy axis. And so if we go 2 in the real, and we call this the real direction, the x direction, and the vertical direction is called the imaginary direction. So if we go 2 in the real direction, followed by 3 in the imaginary direction, we will come to the complex number 2 plus 3i. So you can see as a geometric object, these two things are really the same. We're just labeling the points slightly differently. All right, so just for some practice, let's plot some points. I already did 2 plus 3i. So 2, here is 3i. So here is 2 plus 3i. If I do minus 2 times 2 plus 3i, that's a special case of multiplication. the real part and the imaginary part will each be multiplied by -2. And so the displacement vector from the origin will be -2 times the displacement vector for 2 plus 3i from the origin. So I end up at -4 minus 6i and this was just like scalar multiple. This is equivalent to what you would do in the vector space R2 if you multiplied the vector 2, 3 by -2 to get the position vector of -4, -6. 2 minus 3i lives here. And as in linear algebra, we go back and forth between point representation and position vector representation in the complex plane like we did in R2. Now, if I do 2 plus 3i times 2 minus 3i, for the real part I'll get 4, and then I'll have -9i squared, which is +9, so I'll get 13. And the imaginary parts cancel. I'll get 6i minus 6i. So the product is the pure real number 13. All right, and so a good portion of today we'll be trying to figure out geometrically what that number 13 has to do with the complex numbers 2 plus 3i and 2 minus 3i, whose product it is. Okay, so the arithmetic axioms for complex numbers are just like they are for real numbers. They are the same field axioms. So they can be broken down into the addition axioms. And as we were seeing, complex number addition just corresponds in the identification of the complex plane with R2 to vector addition in R2, because when you add two complex numbers, you're just adding the real parts to get the new real part and adding the imaginary parts to get the new imaginary parts. So we know these axioms without even thinking, although we could check them very quickly. The multiplication axioms are just as straightforward algebraically. I'll make you check at least one of these in your homework. So for example, if you wanted to check that ZW always equal WZ, you could write down ZW and WZ, and then you could multiply out, and you'd see that the real parts on each side agree, and the imaginary parts on each side agree. So the complex numbers in the products on each side agree. So the real part is x1, x2 minus y1, y2. And the imaginary part is x1, y2 plus y1, x2. And I'll let you finish checking that that's exactly what you get if you compute the product in the other order. Okay, so that's the same for the multiplication axioms for all three of them. you have the distributive property of multiplication over addition, which you also have for real numbers. And then finally, you have the axiom that makes this a field instead of a commutative algebra, which is that every complex number has a multiplicative inverse, every non-zero complex number, z inverse, so that z inverse is 1, and we write, because our multiplication is commutative, we write the inverse as 1 over z. And then, therefore, also you can compute quotients of complex numbers. W over z just means w times the multiplicative inverse of z, and in particular, z over z is just z inverse is 1. Okay, so let's talk a little bit about that multiplicative inverse. So here's an example. I wrote down that the multiplicative inverse of 2 plus 3i is 1/13 times 2 minus 3i. So let's just check by computing 2 plus 3i times this alleged multiplicative inverse. We're supposed to get 1. Okay, well, this 1/13, I can put it anywhere I want in the product, so let me just take it out to the front. And then you'll see that when I do the product, I'll get 4 plus 9 for the real part, which is 13. And the other two terms, the I coefficients, cancel. I'll get 6i minus 6i. So for sure, a multiplicative inverse of 2 plus 3i is 2/13 minus 3/13 I. Okay, so there was not magic there, but there was use of the conjugation operation. So I'll explain how I knew what the inverse was almost right away. Complex conjugation, which corresponds to reflection in R2 across the horizontal axis, is you replace x plus iy with x minus iy. And we call that conjugate, we might say the conjugate of z, but for short, we'll usually say z bar, and we'll write it as a z with a bar over it. Okay, so if z is x plus iy, then z bar is x minus iy. The modulus of a complex number x plus iy is just the magnitude of the corresponding vector in R2, so it's also the distance from the origin to x plus iy in the complex plane, the Euclidean distance. It's the square root of x squared plus y squared. Most complex analysis books call this the modulus. Our textbook just calls it the absolute value, and that's quite a reasonable word to use because it generalizes absolute value for real numbers, for purely real numbers. Okay, so conjugation has some algebra properties. If you take ZW and then take the conjugate, that's the same as the product of Z bar with W bar. So let's just quickly check this one. It's completely straightforward. so I wrote in brown here what we're trying to check. If I first multiply x plus iy times u plus iv, and then take the bar, well, if I multiply them, I'll get xu minus yv plus I times xv, xv plus yu. And that is xu minus yv minus I times xv plus yu. Whereas if I work on the right, x plus iy bar is x minus iy times u plus iv bar is u minus iv. And that gives me xu. So I'll get a minus I times a minus I, which is a minus, minus was a plus, which is times I squared. So that's actually minus yv. And then the imaginary parts are, there'll be an I times minus xv plus yu. And that agrees, if you just stare at it for a second, with what we had on the right. If I put my signs right, it's minus xv minus yu. Okay, so that's very important. And also important is the fact that we can express the absolute value in terms of products and conjugation. So ZZ bar is just x plus iy times x minus iy, which is x squared minus I squared. Y squared is plus y squared. And the imaginary parts cancel, so we get 0. So ZZ bar is x squared plus y squared, which is the absolute value of z squared. And if I take square roots, it's always true that the absolute value of z is the square root of ZZ bar. Okay, so as a consequence of those two properties above, the modulus or absolute value of a product is the product of the absolute values. And the quick way to check that is that the modulus squared of ZW is ZW bar by definition, or by what we just checked, and then by the product property for conjugation, that's ZW Z bar W bar. Multiplication is commutative, so that's ZZ bar WW bar, and that's modulus Z squared modulus W squared. So if you just take the positive square roots of both sides, you get the product property for modulus. Okay, so finally, that gives us a quick way to compute multiplicative inverses. So if I want to find 1 over z for a non-zero z, I just multiply by z bar over z bar. And remember, over means multiplicative inverse. So z bar over z bar, you're just multiplying by 1. And 1 times 1 over z is 1 over z. And then you just multiply these two complex numbers, and you get z bar over z bar, which is z bar over modulus z squared. So for example, in the original inverse computation, if I wanted 1 over 2 plus 3i in standard form, I just multiply by 2 minus 3i over 2 minus 3i. That gives me 2 minus 3i over 13. 4 plus 9. Which is the formula that we were given. Okay, so as I've already said, complex number addition corresponds to vector addition in R2. Complex number multiplication looks kind of weird if you're just looking in R2. So the question would be what that point on the right has to do with the 2 points on the left. Polar coordinates explains the mystery. Remember polar coordinates from multivariable calculus? Every point in R2, every point xy, can be geometrically expressed in terms of its distance r, which is the square root of x squared plus y squared, from the origin, and its angle theta in radians from the positive x-axis to the point where the positive direction is the counterclockwise direction. And the identity relating xy to r and theta is that xy is r times the unit vector cos theta sine theta. On the unit circle. Okay, so in the complex plane, so that's in R2, relabeling and thinking of the complex plane, we can write any complex number z, x plus I, y, as r times the unit complex number cosine theta plus I sine theta. And we have special language for polar form in complex analysis. Well, r, that's what we were just saying was the absolute value or the modulus of z. So that's often the language we'll use. And for the polar coordinate angle theta, we'll call that the argument of z often, or arg of z for short. And as always, it is uniquely determined up to an arbitrary integer multiple of 2 pi. Excuse me. Very often, we'll just have theta go from minus pi to pi, but sometimes from 0 to 2 pi, or sometimes we'll make different choices for what arguments we want to use. Okay, so here is the geometric meaning of multiplication. If you've never seen it before, it's pretty cool. So if you have two complex numbers, z, which has polar coordinates r and theta, and w, which has polar coordinates rho, and phi, then the polar coordinates of z times w, the radius is r times rho. So the new radius, or the new absolute value, is the product of the absolute values of z and w. And the new argument is theta plus phi. So the polar coordinate angles add and the moduli or radii multiply. And it's just a one-line proof once you put things into polar coordinates. So let's do it. ZW is R times cos theta plus I sine theta. That's Z times rho times cos phi plus I sine phi. That gives me R rho, and then let's compute the real part of the trig product. So first times first gives me cos theta cos phi. Last times last gives me I squared, or minus 1, times sine theta sine phi. The imaginary part is, first times last is cos theta sine phi. Last times first is sine theta cosine phi. And using two of the three fundamental trig identities, the third one being the Pythagorean theorem, you immediately recognize the real part as cosine theta plus phi from the addition angle formula for cosine. And the second part is the imaginary part is the sine of theta plus phi. I see a typo. It was cosine of theta times the sine of phi. And that is the proof. Very short, and we will use this geometric meaning of multiplication a lot in this class. The multiplication property is especially concise if you recall Euler's formula from 2280, which is that e to the I theta is cos theta plus I sine theta. That was actually a definition of e to the I theta, motivated by Taylor-Maclaurin series. But using that notation, you can write z in polar form as its radius, which is the absolute value of z, times the cos theta plus I sine theta is just e to the I theta. W is absolute value of w times e to the I phi. And then when you compute z times w, this is what we did on the previous page, you get modulus of z modulus w times, and the product of those terms, which were e to the I theta and e to the I phi, just gave us cosine theta plus phi plus I sine theta plus phi. And so this is exactly the computation on the previous page, just using the definition of e to the I theta to go from trigs to exponential. And then the formula makes total sense. It's just equivalent to the rule of exponents for e to imaginary numbers. So what we showed on the previous page was that e to the I theta, e to the I phi is e to the I theta plus phi. Let's end by just illustrating multiplication in one example. So we're going to focus on 1 plus I, which lives in the complex plane. Its absolute value is square root of 1 plus 1, which is root 2, and its argument is pi fourths. It's polar coordinate angle. Okay, so 1 plus I is, so it's root 2 cos pi over 4 plus I sine pi over 4. Each of those are 1 over root 2, which is why we get 1 plus I. But the way we want to write this in polar form is go right to exponential form. This is root 2 e to the I pi over 4. Okay, so let's compute 1 plus I squared in Cartesian coordinates. I get 1 plus I squared is minus 1. And then I'll get plus I, so that's 2I. So here was 1 plus I. 1 plus I squared is 2I. Okay, now if I had done root 2 e to the I pi over 4 squared, I would have gotten root 2 squared, which is 2. E to the I pi over 4 times e to the I pi over 4 is just e to the I pi over 2. E to the I pi over 2 is cos pi over 2 plus I sine pi over 2 is just I. So we get 2I. So notice that for 1 plus I, and we saw that from the green Cartesian computation as well. So 1 plus I squared has twice the polar angle, which is pi halves. Which is 2 times pi fourths, and its absolute value, or modulus, is root 2 squared, the modulus squared. Okay. And if I do 1 plus I cubed, that's 1 plus I times 1 plus I squared, so times 2I. So that's minus 2 plus 2I minus 2 plus 2I is here. And in polar coordinates, its argument is a 3/4 pi. Its modulus is 2 root 2. So in polar coordinates, it's 2 root 2 e to the I 3 pi over 4. And that's what we would have gotten if we had just started with 1 plus I, which was root 2 e to the I pi over 4. And if we had cubed it, the modulus of the product would have been root 2 cubed, which is 2 root 2, and e to the I pi over 4 times e to the I pi over 4 times e to the I pi over 4 is e to the I 3I times pi over 4. So using polar form, gives us the same thing. Okay, so finally, 1 over z, let's do it up here. One over 1 plus I, to compute it, we multiply by 1 minus I over 1 minus I. That gives us 1 minus I over 2, which is 1/2 times 1 minus I, 1 over z, one over 1 plus I was 1/2 1 minus I, or I could have done it in polar form, 1 over root 2 e to the I pi over 4. I could multiply by e to the minus I pi over 4, e to the minus I pi over 4, and I would get 1 over root 2, and that's the product of the exponentials in the denominator is 1 because of the computation we did before, that e to the I theta, e to the I phi is e to the I theta plus phi, and e to the I 0 is e to the 0 is 1. And then I have e to the minus I pi over 4. So in polar coordinates, 1/2 times 1 minus I is 1 over root 2. And for the modulus, which you could check in Cartesian, and as you can see, the polar angle or argument is minus pi fourths. Okay, so we shall continue this discussion, but what we've done today is talked about the complex plane, addition, multiplication, reciprocal, and to get reciprocals we used conjugation. To understand multiplication, we use polar form. And to make it especially concise, we use Euler's definition or Euler's formula. And just to emphasize, You multiply two complex numbers, their absolute values multiply, and their arguments add. Okay, that's the end.